Hello everyone. We are going to solve some of the problems in the chapter 13. Chapter 13 is, as you might know, uh, is electromagnetic induction. So electromagnetic induction is is described by the Faraday's law, and it is related with it's relating the electromotive force with magnetic flux. These are the electromotive force in volt. So in other words, it is an electric potential. And the magnetic flux is defined by the surface integral over A. So if we have a kind of a loop, and we can define the surface, and then we are uh, integrating all the magnetic field through these open surfaces. So this is the magnetic flux. So note that it is the minus sign. The electromotive forces is opposing the change in time of the magnetic flux. So note that magnetic flux has both magnetic field and area. So the magnetic field and times area. So you have a different cases. One is the magnetic field is changing function of time for the fixed area. And the other case is that area is somehow is changing, and for the given fixed d. So we have this is kind of a moving induction problem. And this is kind of a fixed induction problem. So you need to know what to do for these two cases. We will look at these two situations one by one. A square loop. So if you look at it, a square loop. So loop is given, uh, made of a copper wire with a cross-section radius of 1.4 millimeter. If a magnetic field perpendicular to the loop is changing, so note that magnetic field is changing at the rate of this. What is the magnitude of a current in the loop? Note that rho is given. Rho is the resistivity. So we have a fixed loop, and then the magnetic field is changing, so that it will induce the electromotive force around the loop. And then if there is E is found by minus d phi m over dt, then once we know the E, electromotive force, and then we can find out R, which is usually given by rho times L over A. So area of the wire A, and then you have to have the length of the wire with the given resistivity, and you know what it is. So note that the EMF force is in terms of, is given in terms of a voltage, so we can apply the Ohm's law. I is given by IR, so we can find out I, okay, the current, okay. So let's try to find out what is given. Uh, square loop side is given. So square loop A, A, and radius of copper wire, this one. So if you cut it, then you'll find out that it is like this, and then its radius is R. Okay. And the rate of a magnetic field, a change of a magnetic field is given by dB over dt is given like this one, and the copper resistivity is given like this. Okay, so these are the given. So first thing is that we need to find out the magnetic flux through the loop. Flux is given by magnetic field times A. Note that magnetic field is perpendicular, so that if you think about so these are always perpendicular to each other, so that you get it is actually B, and then you get out, and then you have a dA, then it is B times A. And then we know the area is is a square root, so that A square, so that we know this one. And then Faraday's law indicates that electromotive force is given by this one. And then in our case, area doesn't change. Area is fixed, but only the magnetic field is changing as a function of time. Okay, so we can plug in this one. And then so from this relationship, we are given something volt. Okay. And then next thing is that we need to find out the resistivity. So total length is 4A. So way A. So it's A is the total length of the wire. And the cross section is given by this one. And then resistance is given by this way. So we now know the resistance for this loop, and we also know the electromotive force. So electromotive force is a volt. R is given in terms of ohm. And then volt over ohm is going to be ampere. Then you can find out the current. So it's a combination of Faraday's law plus Ohm's law. Now we have another problem. So in this case, magnetic flux is given as a function of time. Okay. And then it is asked that what is the magnitude of a current through the loop. So in this case, we note that magnetic flux through the loop is given as a function of time. Here's a t, and there's another t. Okay. And then we are also given that resistance is given 3 ohm. Okay? And we want the current through this circuit. What this is R. And we want to know what is the current at t equal to 0. So that's the questions. And then we have to start with Faraday's law. So we need to find out electromotive force around this loop. Okay. And then we note that it is given by this one. So d phi m dt is already given. So because phi is given, so if you take the derivative, it has a function of a t here. So ft times the gt. Let's say ft is t and gt is sine omega t. Then d phi dt is given by f prime t gt plus ft g prime t. Okay, is the derivative. And then you have a two terms. These are the two terms. So if you take the derivative, it is going to be 1, so that you have only this term. And then ft stays there, t. And then if you take the derivative, once again, you get cosine. Okay. So that's the way it is. And then if you take the derivative of a sine, you become a cosine, right? And then you should add, you should multiply this coefficient in front of it, right? So we know what the derivative is, and then we can find out electromotive force by taking the absolute value. Okay. And then we need to evaluate those value at t equal to 0. And we note that cosine 0 equal to 1, t equal to 0, it becomes 0, so that this term is going to be 0 when t equal to 0 because of this t. And then the only thing you can get is this term. Okay, let me just take about it. So it is this term, then cosine. Okay. Then we need to take the absolute value, and for t equal to 0, and you can do the calculation one by one. You will find out this is the value. And then it is related with the electromotive force, your electromotive force. And then current is given by electromotive force divided by the resistance, which is 3 ohm. Then you can get this one. Okay, so here what we have done is that, so we are given, there's a, sorry about this. This is wrong. There's exponential minus 3t. So I think that this part may be wrong. So let's do it once again. So it's exponential minus 3t, so that exponential t sine at. So if you take the derivative, say minus 3 exponential minus 3t sine t plus exponential minus 3t times a times cosine at. Okay, so what is happening is, I think that this is wrong. I think that this is wrong. This is c. So if you have a exponential term and sine t, and then you want to have evaluation at the t equals 0, and because of sine, this term goes to 0. And you get this term is left over. Okay. And then at t equal to 0, exponential minus 3t is exponential 0, and it is 1. Okay, so basically it is given by cosine at times a. Okay, sorry about this. There's some mistakes. Okay. But the result is the same. So basically you have there was a cosine 0. Okay, and then you get this value. Okay. Now let's go to the another problem. This is a little bit different. Okay, so it is kind of a motional electromotive force, but it is not a closed loop. Thus far, what we have seen is a kind of a circular loop or rectangular loop or square loop, but now we have just a rod. Rod, that's the big difference. The rod, metallic rod. And then it is moving. It is moving over uniform magnetic field. That means magnetic field doesn't change as a function of time. But this rod is moving with the velocity, constant velocity. Then what's going to happen? Then what's going to happen? Then we have to think about the situation. So magnetic field is constant and uniform. And the velocity of rod is given. Length of the rod is given. Okay. And then what we need to do is that we have to think about the rod is consists of electrons. Okay, many electrons. And then when the conductor moves through a magnetic field, free charges here, say this electron. So all of the electrons inside, I'm sorry, all of the electron inside uh, so let's assume this one. This moves with the velocity v, and this also moves with the velocity v, and this also moves with the velocity v. And then, using the Lorentz force, each of the charge is moving with a constant velocity in this direction over the uniform and constant magnetic field. And then it will feel the Lorentz force, which is given by QVV. And then in this case, velocity and the magnetic field is orthogonal to each other, so that F is going to be QVB. Okay, so there you have a force. In other words, if you think about magnetic field is pointed toward you, so let's try to charge, and the magnetic field is here, and the velocity is there. And then if you think about the magnitude is QBB, V cross B will move the charge. If it is negative charge, then QBB will be this direction, upward. Okay. So what is happening here is that by moving a movement of the rod, you will have a negative charge on the top, and then by charge neutrality, you will have a positive charge like that. And then that means there is a potential difference, electric potential difference. Okay. And then it is related with the over length L. Okay. Right. And then what is happening here is that each of the movement of the electrons, and you will build up the potential like this. Okay? So in other words, you will have a charge separation by this one. You have a electric field, right? And then this force is nothing but Q times E. So electric field. So what I mean by here is that by Lorentz force, you build up the separation of charge, and then you have electric field built in, okay? And then electromotive force is actually E times L is your voltage. In fact, it is given your electric potential. So, and then from this, we note that electric field is actually minus gradient phi E. Okay, so this is the integral form, and this is the derivative form. But anyhow, in this case, you get the charge separation to build up the electric field, and then this electric field times L, the length is going to be your potential, and this potential is EMF. Okay, and then what is E? E is given by, if you just take VB, okay, and if you recall, it is very similar to what we have observed in the Hall effect. Hall effect. And then you have a correlation between the built-in the electric field and the external magnetic field like this. And then eventually your potential EMF is E times L. E times L is VLB. Okay. This formula is very important in the next problems as well. So what is happening here is that the potential difference between its end here, here, and here, is corresponding to here and here, is given by BLB. So what is happening here is that not directly related to Faraday's law. You need to think about it is not directly related with Faraday's law because we did not calculate any magnetic flux. Simply because we did not have any loop. But instead, we are using Lorentz force. Okay, Lorentz force. And then we find out the electric field, and from the electric field, we find out the potential difference, and that potential difference is going to be our electromotive force. Okay, so you need to understand the differences. So electromotive force could be achieved using the loop, but also it could be achieved with the moving rod. Okay, moving rod. So now we have another cases here. The rails connecting end piece and the rod all have a resistance per unit length of 2 ohm per centimeters. Okay, resistance given. The distance between rod is 4 centimeters, and the rod moves to the left at the velocity. And the magnetic field is uniform and constant. You are to find out the current when A equaled 8 centimeters. Okay. So what we have to think about is that so magnetic field is constant and uniform. It doesn't change with the time. But the rod has a velocity, and then distance between the rail is 4 centimeters. Okay. And this distance between the rod and the connector is given by this A. Okay. And resistance per unit length is given by this one, unit length. So now let's build up our logic. So in this rod is moving, so that we have in previous cases exactly same cases. So in this case, rod is moving these directions, but in this problem it is in the other way. But what we need to understand is that by moving this one, we have a potential difference from to here. Here is given by this. That is important. And then what is going to happen here is that we have a EMF force, which is the voltage difference, which is the same as the voltage difference between this part, and this part. Okay. So that means it works as a kind of a okay, like this. So total length is so 2a plus 4 centimeters is the length, and then this will serve as a resistance, and this is the EMF. Okay. So what we have is that a plus 4 plus 4. So this is the rod also has a resistance, and that these wires have a resistance as well. So the total length is 24 centimeters. And then the resistance is given by this one for unit length times length. Okay. And then you will get the ohm. And then we have everything. We know what the potential difference is, and we know what the resistance is. So the key point is that you need to realize, okay, this part of the problem is equivalent to okay, so EMF, and this EMF is caused by the motional EMF. Okay, and this one, and then this all is going to be uh, total length times resistance per unit length, and then you can find out resistance. And then once you know what the resistance in the electromotive force are, then you can find out I using Ohm's law. So once again, it is a combination of motional EMF plus Ohm's law. But note that we did not use the Faraday's law, because what is happening here is that uh, uh, we have this rod, and then uh, we are going to assume that we have this electromotive force is only on this rod, and then we have equivalent circuit like this. Okay, that's the key point. And now let's try to find out another type of case, but in this case it's a moving loop. So previous cases we have a moving rod. So let's try to find out what is different. So it is given, the side length of the square loop is given, L is given, and the velocity of the loop is given, and magnetic field is given. And then now we are using Faraday's law because it is a loop. And the Faraday law states that your magnetic flux change in time will give you the electromotive forces. So for these cases, you have a area A, and then you have a magnetic field. Note that magnetic field uh, direction and uh, surface normal vector is the same, okay? Or opposite, you may say that, but it is parallel. It's parallel, so that you get the magnetic flux is given by your magnetic field multiplied by the area of the loop. Okay, and then you get the electromotive force given by B doesn't change with the time, only the A is changing with the time. So in this case, the loop moves into the field, and you get L times X. This is your magnetic field, and this is your X, and this is your L. So it is moving. That means your area is going to change. The where the magnetic field is passing through is going to change because X is given by dx dt is given by this one. So that if you take the derivative, L doesn't change, only the X is going to change, so that we have dx dt. And then we get dA dt is given by this one. And now, if you just plug in B times A t, and then it is nothing but B times dA dt, and it is E times L times V. So it is, once again, it is also interesting to find out is BLB, even though uh, it is exactly same time, same formula as the moving rod. Okay, so moving rod over length L, and moving square O length L, they have the same electromotive forces given by this one. Right? And now another the next problem is quite interesting. So let's try to think about it. I just added the picture here. A metal disc in a radius, this is rotates about its circular axis like this. This rotate with an angular speed of this one, omega is given, and the disk is situated in a uniform magnetic field. This magnetic field is a uniform and constant. And then what is asked is that what is the absolute value of the induced voltage between the axis and the circumference, the rim? So they are trying to find out what is the voltage between the rim and the center. Okay, like this. They want to find out voltage here. Okay, and this is called Faraday disk, and it is called homopolar generator. And then homo means is that single pole generators. When the disk rotates in a magnetic field, the charges in the disk experience Lorentz force. Okay, Lorentz force, and then we know that what the Lorentz force is, QB times B. And the direction of the force is such that this pushes charges radially, creating potential difference between the center and the rim. So remember that in the case of the rod, it is moving in a linear velocity with a certain b. Then you generate the charge separation at the ends of the rod. Okay, but what is happening in this case is that if you have a magnetic field, constant magnetic field, and then you rotate the conductor, and then you have a charge separation, plus or minus, like that, depending upon your rotation directions. But anyhow, you can build up the potential difference from center to the rim. Okay, from center to the rim. And it is, once again, it is based upon Lorentz force. So the radius of a disk is given r, angular velocity is given omega, and the magnetic field is given b. Okay? And motional electric field is given by, so at a point at the radius r, yeah, moves in the tangential velocity, v is omega times r. This is a circular motion. So when you go back to physics 161, if you have a circular motion with the angular velocity omega with the radius r, then the velocity is given by v is r omega. Okay. And then Lorentz force produces the electric field, okay, by charge separation, right? This charge and a negative charge like this. And then it is given by this one. Note that this force is same as QE. Okay. And then from this you get this relationship. Once again, it is very similar to Hall effect formula. But anyhow, in this case, V is given by V is omega plus R, omega times R. And then we note that the electric field is depending on the radial position. So we need to take the derivative over we take the integral of the electric field over the path, and then this will give you the potential. What is this? Okay. And in this case, electric field is along the radial direction, so dl becomes the dr. Okay. And then if you just plug in electric field here, then we found out that it is dependent on R, so that we get this formula. So we have voltage like this. And then we just plug in the magnetic field, omega, and the R, and then we get the voltage. And this device is historically important. It is the first electric generator invented by the Michael Faraday and is called homopolar generator. Unlike AC generators, it produces direct current, okay, because the polarity does not reverse during the rotations, okay. So even though it is rotating, it does not change the polarity, so that it is called homopolar. Homopolar. And now this is another example of a generator. You'll see that it has a AC, not the DC cases. So we have this loop, and then it is being rotated. And instead of the circular plate, we have a kind of rectangular loop. Okay, and then its position is changing, its angular position is changing, and then the given is number of turn is this, magnetic field is given by this one, dimension of a coil is given by this one, time interval is zero point 0.8 second, and then theta 1 initial angle is 30 degree, and the final angle is 70 degree. So from this you can find out the omega, so angular velocity. But anyhow, so let's try to find out what you can get easily, which is the area of the coil. Okay. And then magnetic flux is going to be calculated with this one. Note that this product. So if you look at closely, then if you have a magnetic field here, but if you look at it on the top, and then it looks like this. And then in this case, your n normal vector is not parallel to this one. It is making a certain angle, okay, theta, and then it becomes a cosine theta, okay. In other words, if you have n turns, then you should multiply by this one, and then becomes NBA cosine theta. And then Faraday says that is d phi dt. And then in what we have found is that delta t over delta phi. Okay, so that during the time interval, angle is changing from the theta 1 to theta 2. So we can plug in theta 2 value here and theta 1 value here. Delta t is given by 0.8 second. So every value is known. N is known, magnetic field is known, A is already we calculate here. Theta 2, theta 1 is are known, and the delta t are known. Then you can find out electromotive force on the this one. Okay. Okay, so that once again we're going back to the moving conductor cases. So at what speed must the sliding rod in the figure below move to produce electromotive force over this one? So in this case, electromotive force is as unknown, and then we need to find out what the velocity. So electromotive force is given, magnetic field is given, length of the rod is given, and length of the rod is given. Okay, and we note that motional EMF for this kind of rod is given by EMF is VLB. Okay, and then from this we find out velocity is going with V epsilon over PL. E is given, L is given, the electromotive is given, so that we can find out the velocity. Okay. So once you know the EMF for the moving rod, which is this formula, then you can find out velocity fairly easily. Okay. And similarly, we can extend our viewpoint from the rod to the airplane. So calculate the average induced voltage between the tips of the wings. Here, the airplane is moving this way, so that between the tips of the wings. So we want to find the voltage difference between the wing. Okay. And it is flying with this velocity. The downward component of the magnetic field at this place is this much. So that magnetic field is here. So in other words, it is equivalent to the magnetic field here, and then we have a moving rod. Okay. So that's what you are going to assume. Okay. Here is the wingspan span here. Here to here is the D. D is given by this one. Magnetic field is given, velocity is given. Okay. And the only thing we need to worry about is the dimensions, the units. Kilometer per hour should be converted into meter per second. Okay, so that we have a meter per second in velocity. And the motional EMF for this kind of rod is LB actually. And then L becomes the D in this case. And then we can find out electromotive force like this. It is order of a kind of a 1 volt. You will, if you do it, calculate. So the airplane wings behave is like a 47.5-meter long conductor moving through the Earth's magnetic field, right? And it's moving. Okay. And then you can measure the potential difference between these two wingtips. This is about order of 1 volt. Okay. Now let's try to see another case. This is a little bit interesting. The figure shows a copper rod moving at a velocity. This is the velocity is given, right? And parallel to the long straight wire carrying a 6.8 ampere current. So that I is given ampere. And calculate the magnitude of EMF induced in the rod. So the first thing is that if you have if you have a current carrying wire, that means you have a magnetic field. That's the first thing we need to know. So instead of a uniform magnetic field, now we have a magnetic field is changing as a function of the radial distance from to here. Okay, so that's the key thing. So magnetic field from this long straight current wire carrying wire, this is the magnetic field. And then we need to find out motional EMF produced in the moving conductor. That's the problem. So velocity is given, current is given, and the distance A, distance B is given. In other words, is, yeah. And we get the mu zero is given. The first thing is that we need to find out what are the magnetic field across this rod. So that at a distance r from the current I with the r, BR is given by mu 0 I over 2 pi R, right? Can use Ampere's law to calculate this one. And then the rod spans distance from A to B from the wire, from A to B, okay? So in other words, R goes to A to B wire. And that's the range the wire, the rod will fills the magnetic field, okay? So what we are going to do is that we are going to have a small segment of dr, and for this dr, we get electromotive force dE is going to be V times B times dr. That is similar to BLB, and then L becomes dr. Okay, that's the key thing. And the BR is a function of R, and then if you just plug in, then we get this one. And then once we get this relationship, and then you can do the integral. And once you get this position, and then our electromotive force will be integral from R equal to A to R equal to B. Okay, this will cover the rod. R equal to A to R equal to B. Okay, and then 1 over R, integral of the 1 over R is log. And then our EMF is going to be this form. Okay, and then you can find out electromotive force in a numerical value. So important thing here is that our magnetic field is constant in time, but it's not uniform. It varies with 1 over R. So we have to make an integral along the rod. Okay, so we have to change from the uniform magnetic field case to d epsilon is VR. In this case is the V times dr. Okay. The only constant factor is the velocity v. Okay. And then this is our starting point, and the BR is given by 1 over R. Okay, so that we have this log term. Now let's try to find out another problem. So now we have a square coil, and the number of loops is also given. And then it is quickly pulled from the field at a constant speed, okay, moving perpendicular to the magnetic field to a region where B drops abruptly to 0. So B equal to 0 region, B equal to non-zero region, and then it is moving to this one. So apparently what is happening here is that your magnetic flux will change across this loop. Initially, it filled with the B, but as it moves, then you will have some part will be filled with the magnetic field, but some other field is no magnetic field. Okay, so that your magnetic flux will change. That's the key point we need to understand. So given is the loop length and number of turns magnetic field is given by Time to completely leave the field is that delta t is given by this one. Resistance of a coil is given by this one. Okay. The area of the square coil is given by area is a squared, and then you get the area. And now it's time to think about phi, which is given by n times b times a. Okay. Then initially coil is fully inside the field. Okay. But the final flux, it is completely outside. So initial is NBA and the final is just outside, completely outside. So that there is a flux change. Okay. Delta phi is given by this one. And by this Faraday's law, our electromotive force is given by this d phi over dt. And then it is given in terms of delta t. And then we know that delta t is time to completely leave the field is delta t. Okay. So we know what the delta t is, we know what the n is, we know what the b is, we know what the a is, and then we can find out the electromotive force. And then after that, once we find out the electromotive force, for the given resistance, we can find out the current. Okay. So you will find out that there are several types of problems. You need to find out the electromotive force, and then using the Ohm's law, you can find out the current. Okay, that's the kind of typical examples. Okay, that's it.